Today I'll be talking about vector search. What is vector search? How do we use it in a lot of these potential applications around semantic search? And why does it really make sense? What are some of the different ways that companies, organizations, individuals are using vector search today, right? So, as I mentioned, I'm an architect here at Zilliz. This is my email, my LinkedIn. Feel free to get in touch with me on social media and on GitHub as well. Yeah, and a little bit about Zilliz. I did mention this already, but we are building what is called a vector database for enterprise-grade AI. And the idea behind a vector database is that folks want to be able to do a lot of productionization of their vector search. I won't get too much into this right now. Happy to take more questions about Zilliz at the very end. And a little bit about Milvus as well. Milvus is the vector database, the open source vector database that was created at Zilliz. And it is, we are open source and we are a very, very rapidly growing community. So welcome. So a bit about what we're going to talk about today. So first, I'll go over what is unstructured data and what are embeddings. Right? And I think if you look at vector search, if you try to understand, if you look at vector search just as a word, right? If you say, I want to be able to search across many different vectors, it doesn't really make sense unless you have a bit of context about how it works relative to machine learning, relative to modern AI, and using embeddings. I'll then take a bit of time to talk about vector search itself. How do we do it, especially at million or billion scale? I'll go through some demos, specifically some notebooks, some tutorials I've put together, and these will be made publicly available on GitHub. So feel free to go download them, play around with them yourselves. And then I'll talk about some real world use cases. So what are some of the interesting ways that folks are using vector search today, right? And why does it make sense for you to really go and try to understand vector search and play around with it? First, talk a bit about unstructured data and embeddings. And I do realize that for some folks here, it might be more of an introductory topic, but I think it would be good to go over so that we have a good baseline understanding of what the motivation behind vector search really is. And if you look at unstructured data is any data that is not conformed to a predefined data model. Now, what does that mean, right? So some great examples of unstructured data are images, video, audio, text, anything that you can really use machine learning to process, that you can really use ML to do, let's say, image recognition or semantic or different types of natural language processing tasks, question answering, so on and so forth. But there's also a lot of great examples of what I call less boring examples of unstructured data as well, such as geospatial data, IoT data streams, molecular structures, so on and so forth. And if you really look at the evolution of data, we start off in a very structured way, right? And we started off in these, very relational databases, table-based databases, and we moved to sort of NoSQL databases, wide column stores, key value stores, object databases, and now, as we entered the IoT era, as we entered the area of having large amounts of compute power and storage resources, data has become more and more unstructured. And we really need a way to be able to store, index, and search all of those pieces of data. And the way that we do it today, or the best way I would say that we do it today, is with deep learning models. Now, this image here is very, very highly simplified, but I think it should hopefully give everybody a bit of background about how vector search works, why vector search is important. The idea that we have so much unstructured data today, and we use these trained ML models to generate embeddings for them, and to allow computers to understand unstructured data in the same way that we do, right? All right, great. So now that I've gone sort of some of those bits out of the way, I do want to sort of talk a bit about what unstructured data can be, or excuse me, what these embeddings, what these vectors can be used for. So you see up here on the left, these are actually digits. And what we've done here, I suppose the author of these images has done here, is actually take these digits, run them through a neural network model, in this case a ConvNet, take the embeddings and find the nearest embeddings in a data set of these images, related, as closely related as possible to the query image. So you can see in this case, the top row is simply a variety of 2s. Second row is a variety of 6s, 7s, 8s. You do see a bit of 5s in there, but semantically, these 5s are written in a very similar way to these 8s, and 6s at the very bottom. These are again, as I mentioned, the nearest neighbors in this high dimensional vector space to these input digits. Here's the same thing for food, right? I think it's good to, I hope nobody's hungry right now, but I think it's good to visualize exactly how this nearest neighbor search works, exactly how these embeddings work that are generated from these machine learning models. Again, here you see the same thing, where you have query images on the left and images that are a part of the data set on the right. Images that you see on the right are really the nearest neighbors in this vector space to the query image. You can do the same thing with words, right? So you have, for example, at the very top, you have sort of more, these are embeddings generated for individual words. At the very top, you have these sort of more, I'm not sort of in this particular space, but you have more scientific words, molecules, proteins, ions. At the bottom, you'll see a lot of names: Chris, Frank, Lee, Tom, Gary, Phil. And on the right, you'll see a lot of these processes, a lot of functions. And really, this is a word cloud that's generated in the TensorFlow, I believe it's called TensorFlow projector. And it really goes to show you the power that vectors have, not just in images, but also for text as well, and for many, many other modalities. And vector search can really be used across, as I mentioned, images, video, audio, natural language, and also less mundane examples of unstructured data as well. Geospatial data, molecular structures, DNA, so on and so forth. So now that we've gone out of the way, I do want to give folks a bit more introduction into how we use vector search today, right? How is vector search done? And especially at million scale, at billion scale, and being able to process, for example, if I'm a large tech company, let's say I'm Facebook, for example, I have all these photos, how do I enable computers to understand them semantically so that I can better help my users? This is a very, very complex problem, right? Vector search is very, very hard. And some of the different ways that we can actually take a step back and talk about how vector search can be done naively. If I have a database of vectors, or if I have a database of unstructured data, I have a huge data set, and let's say it's got a million elements, there's going to be, if I have a query vector and I want to search across all 1 million elements, that's going to take a lot of compute power. And we'll see that in this upcoming sort of notebook that I have prepared here. We'll see that it takes quite a long time. So the way that we typically do it is with what are called indexes, vector indexes, similar to what you see indexes in relational database. And these indexes are really there to speed up your vector search process. The idea is that you have tons and tons of vectors that you want to be able to search across. You build an index or this particular data structure on top of it to enable you to do your vector search much, much quicker than you would be before, right? So here are some different indexing strategies. And, I don't want to go too in-depth into all of these, but just talk very, very briefly about how some of these work. So generally, if I have a vector, if I have the output of a trained ML model, an embedding would be this high dimensional, this dense floating point vector, floating point tensor. And one of the ways I can speed things up, one of the ways I can reduce the size of my index and really speed things up is with scalar quantization. The idea here is that I will take this floating point value and I'll quantize it to, let's say, a number of bins, anywhere. If I'm using, for example, 8-bit quantization, that would be 256 bins. I would put it into these bins and essentially be able to reduce the overall size of my index that way and potentially speed things up as well. I'll go into an example of scalar quantization a little bit later in the tutorial. There's also something a little bit more complex called product quantization. Right? The idea behind product quantization is I'll do the same thing, except I will do it to these subvectors. And each subvector will be mapped to a very particular set of codes. And each code will essentially be a centroid for all of these different subvectors. That doesn't make sense right now. No worries. As I mentioned, I will go into it a little bit later when I pull up the notebook as well. There's also locality sensitive hashing, the ability to say, hey, I have many, many different bins. Perhaps some of my vectors are related, and I want to be able to bin each of these sort of vectors into their nearest neighbors. It's something called locality sensitive hashing there. Approximate nearest neighbor search, oh yeah. One of my favorite algorithms, simply due to the name. This was actually created by Eric Byrne over at Spotify. And the idea is that we create a very, very large tree and continue to split, and each tree, you split into two halves based on a hyperplane that divides two randomly selected vectors. IVF, again, I'm going pretty deep into a variety of different vector search functions here, but IVF is really the ability to take these vectors, create what are called these Voronoi cells, and you see here, each vector would be associated with its individual cell based on these centroids. And also, last but not least, HNSW, or hierarchical navigable small worlds. And the idea here is that, again, we create a graph of these different vectors, and we want to be able to traverse these graphs very, very efficiently. Why did before I go into the next section, before I go into a lot of these notebooks, I do want to mention very, very briefly, why did I go over all of these different vector search strategies? And the reason is more or less just to, go back to my original point that vector search is very, very difficult. There are a variety of strategies, a variety of vector search algorithms, vector search indexes that folks have created to do different things. So to give you an example, product quantization and scalar quantization are meant to reduce the overall size of your index, but they might not be the best choice if you want really, really good recall. When it comes to vector search, a lot of these indexes are meant to really give you approximate vector search, so they will generate an approximate value for you. Whereas if you do want, let's say, great recall, you do want great speed, you would need to use more complex data structures such as these tree-based data structures like Hanoi or HNSW as well. And these data structures, what they'll do is they will, at the cost of memory, at the cost of index speed, they'll give you a really, really large boost in your performance, and they'll give you really close to 100% recall if you tune them properly. But the index will be very large. And in fact, the index for HNSW and Hanoi are actually bigger, larger than the original size of the data set itself, the original number of vectors that you have. So vector search is a really, really hard problem, right? And there's, again, I don't expect anybody to really truly understand a lot of these algorithms just based on this cursory explanation for how some of these vector indexes work. But what I really just want to give folks a really high level overview, really develop a good understanding for why we're spending so much time and why it makes sense to be able to have this created in either a managed service or your own database. Okay, so last but not least, I want to talk very, very briefly about some hybrid indexes as well. You have in Face, for example, Facebook AI Similarity Search, also an open source library on GitHub. You have these idea of what are called primary plus secondary indexes, coarse quantizers plus fine quantizers. Some examples here are IVF plus PQ, IVF plus HNSW, and HNSW plus scalar quantization. And these are all, as we'll see, upcoming different index types that you can use in Milvus as well. So time to get into a bit more of the hands-on portion of this tutorial. So what I'm going to do is, and before I do that, please feel free to visit github.com/fcleavectorsearch and to really access some of the contents of this tutorial. Feel free to go through it, play around with it yourself, and to take a look at what is in there so that you can have a better understanding of how vector search works at a very, very high level. This is a Jupyter notebook that's running in the repo that I have linked online over there. What I want to do first is really talk about some of these indexing algorithms. We just talked about these different ways that you can do vector search and why vector search is very difficult. And here, instead of here, I do have to admit, I had a more complex notebook here, but what I want to do instead is just use this as a starting point, as a launch pad to encourage folks to try these different indexes, to use them in your own machines. And what I've done here is, if you look inside this index folder, in the vector search repository, you'll actually see I've implemented in Python just a variety of different indexing strategies, from flat indexing all the way up to HNSW. And mind you, these implementations are more to enable you to get a better understanding for how these vector search algorithms work, for how vector indexing works in general. They're not meant to, I do not encourage you to put these indexes into production. There are better ways to do it. Milvus, which I'll get into in an upcoming notebook, is one of them. And I'll go over these very, very briefly first. I'll go over flat indexing, product quantization, and HNSW first. But really, as I mentioned earlier, I want to use it more as a launch pad, a starting point for you. If you're interested in vector search, go around, play with these different index types, sort of try it on some of your own data, see how it behaves differently. See how these different indexes behave differently. And then once you are ready to take it to the next step, I would strongly encourage you to use something such as Milvus, production-ready vector database, to be able to put your ANN search in production. So I'll go over these very, very quickly first. I have these implementations here, and I won't go over these implementations in too much depth, but these are really meant for you to just go around, play with it, make some modifications to it yourself, and really try to be as hands-on with it as possible. So flat indexing is the most naive indexing strategy. And essentially what it is if I have a data set of vectors, I have, let's say, 1 million vectors here, the index itself is just the vectors. It's not really a specialized data set that I create over my collection of vectors, right? And the way that I search across these is simply by performing a naive search. So this function will simply loop through all of the ones, all of the vectors that are present in the index, do a naive comparison, and it'll sort of return the nearest neighbors just based off of that. It'll return the closest vectors that you find in a data set given a query vector that you see here. If you use any method that is quantization-based, either scalar quantization or product quantization, if you use any of these quantization-based methods, what you'll do is that you will actually transform your data set into either, if you decide to use, for example, 8-bit quantization, into an 8-bit data set. Perhaps you have 32-bit or 64-bit floating point numbers, you'll transform it to 8 bits. And that is where you will be able to find, where you'll be able to see your speed up. Product quantization is a little bit more complex, where instead of quantizing each individual element of the vector in the entire data set, I instead quantize these subvectors. And again, I'm not going to go too deep into what product quantization is. The idea here is very similar. I want to be able to quantize my data set and be able to search across it, reduce the overall size of the index, and be able to search across it in a more efficient way. And then finally here, I've created an HNSW implementation. And HNSW is the most complicated out of the bunch. The idea behind HNSW is that I want to be able to create a layered graph of vectors, where vectors will point to its nearest neighbors in the individual layers. Some of these individual layers will have longer connections, will have fewer vectors and long connections, and the bottommost layer in HNSW is going to have a lot of independent connections and a lot of, it's going to have the entire data set in the bottom layer, basically. Now, HNSW is probably the most widely used vector search, vector indexing strategy today. And again, similar to PQ, similar to some of these other indexing strategies, I won't go too much into it in detail. Happy to chat with anybody offline, if you'd like. But this is an implementation that I created. It is not, as I mentioned, it's not something that I would necessarily put into production, but it's really there to help you play around, to enable you to play around with these different vector search strategies, maybe make some changes to these algorithms to fit your own needs. Okay, so now that I've talked about some of the different indexing strategies, I'm going to, this notebook is more meant to be a launch pad, a starting point for you to try some of these different indexing algorithms. So I'm going to include these in my search path first. And flat indexing is by and large the most naive indexing strategy. You see that it doesn't really require any, if I'm to create a flat index across 10,000 vectors of dimension 256, it's not really going to take much time. Actually, it's going to take no time at all because the index is simply the data set itself. But if I were to do a search across all of these, you'll see that it definitely takes a little bit more time to, or in this case, it'll actually take the most time to actually run a flat search. If I were to use product quantization, you'll see that in comparison to flat indexing, it actually takes a little bit more time. But once the index is built, I'm actually going to run this search and you'll see that it will actually be a little bit faster than the flat indexing strategy here, right? Well, in this case, it was actually a little bit, it's a little bit embarrassing. It was actually a little bit more, but I probably do have some processes, some other things running in the background as well. HNSW, I'll create this index as well. This index is going to take the longest to create. It will take a long time to run. But at the very end, you will see that when I perform this vector search, when I search for my nearest neighbors inside my HNSW index, it actually takes the shortest amount of time. So what essentially is going on here, right? So for these different indexing strategies, essentially I am moving, it's always a trade-off between the size of your index, how long it's going to take to query, and how long it's going to take to build. And in the case of the flat index that we saw earlier, it built pretty much instantaneously because there was no data structure associated with a flat indexing strategy. With product quantization, I do have an index creation process, but because the index is, and again, this is very, very simplified, but because the index is smaller than my overall data set size, because it is meant to be more of a compression strategy, it actually does take a bit of time, but as you can see here, not as much time as something like HNSW, as a graph-based or more complex algorithm like HNSW. I'm not exactly sure how long it's going to take me to build this HNSW index across 10,000 elements, but when it is done, I will run this and you'll be able to see that, yeah, it is actually the fastest when it comes to querying. And mind you, these implementations that I have here of HNSW, of PQ, of SQ, of flat indexing, they are not the most efficient implementations. I've written them in pure Python using NumPy, obviously. But if you want to do vector search, there are much, much better ways of doing vector search at large scale, much more optimized ways from a compute perspective as well. So this one is still running, and I think it might be because I have some processes running in the background, Zoom, for example. So I will actually come back to this once it's done, and we'll sort of run this again. We'll sort of run this HNSW-based search. And you'll be able to see that it is indeed the fastest strategy at the cost of a large index size and a large indexing time as well. Now I want to go a little bit more hands-on, go into more of sort of, I guess, the fun part of this tutorial. I alluded to earlier the idea that we use vector search to understand unstructured data. And a great example of unstructured data is text, is, let's say, plots. If I have movie plots on IMDb, or in this case, Wikipedia movie plots, this is a great example of semantics, this is a great example of unstructured data that I can perform semantic search across. So this particular notebook here talks about movie search using Milvus, which is, so I will do a quick segue and talk a bit about that first. Milvus is a vector database. It's meant to allow you to do vector search at scale. It's meant to say, if you have a lot of vector data, if you have a large data set of vectors, and you want to be able to do vector search across all of them, Milvus is one of the ways to do it. And as I alluded to earlier, Milvus is what we call a production-ready vector database. And it will allow you to build, it'll allow you to do a lot of these processes, index building. It'll allow you to do a lot of traditional database features as well, caching, replication, failover. It allows you to, it really abstracts a lot of the complexities of vector search away from you, the user. And in this case, you'll be able to see that I'm able to do this in Milvus much quicker and at a much larger scale than I would be if I were to use some very, very simple tools. Once I go back to my slides, I will talk a little bit more about Milvus and sort of about how it differs from vector search or how it differs from just plain vector search using some of these indexes, but I'll get to that a little bit later. I'll walk through this notebook with everyone here. The first thing that you want to do is obviously run this. You want to be able to grab all the dependencies that you need in Python. Grab the data as well. In this case, I already have it, so I'm not going to run this cell. But I've actually run this one as well. But grab the data. We have made the data readily available to everybody here on Google Drive. Download it, and it'll allow you to play with it as well. Now, this part that you see here relates to actually setting up Milvus. As I mentioned earlier, Milvus is what's going to allow us to do vector search at 100 million scale, at billion scale. In contrast, what we saw over here in these examples over here is we were doing it at 10,000 scale. And even here you saw that it definitely takes a bit of time. It takes, doing these vector searches probably not in this fashion is probably not ideal if I have a lot of data. Let's say I have, millions and millions of images or other pieces of unstructured data that I want to run through. And the way that we would do it in Milvus is that we would first simply set up the database itself, set up this database as purpose-built for vector search. In this case, I'm using our managed service called Zill's Cloud. And the reason is more so because I'm lazy in terms of setting up Milvus locally on this laptop. So what you would typically do is you would set Milvus up. You actually have a URL and then a way to simply access it that way. But I'm going to set up those arguments there, and that's really all that. Those are really all the parameters that I need to be able to connect to my Milvus database and to be able to use it. So once I've done that, I'm going to create a connection to the database, and I'm going to create a schema across it. And the schema is really needed in order to be able to add those embeddings to the database, right? So I'm going to blow through these pretty quickly. I'm going to drop this particular collection in the database if it doesn't already exist. And here, what I'm going to do is I'm going to create a schema to allow me to do that vector search that I mentioned earlier at very, very large scale. And then here, there's one thing that I do want to mention. In Zill's Cloud, you actually have what's called auto-indexing. But if you're using Milvus, you have a variety of different indexing strategies. So for example, you have IVF flat, you have IVF PQ, HNSW, Annoy. We also have a disk-based index called disk-ANN as well. And these, you would be able to select a variety of different index types based on what your application needs, based on your requirements. As I alluded to earlier, if you want a smaller index size, but you don't need that much recall, you might want to use something like IVF PQ. If you need really, really good performance, you probably want to use HNSW, so on and so forth. And I highly encourage folks to play around with different settings and to understand how that impacts your vector search, your index creation, your querying process, so on and so forth. So I'm going to create in the next params, I'm actually going to load the collection as well. And this will load the collection in my vector database. And here I'm going to insert the data. And I'm actually not going to go through this step right now here in the notebook, simply because it will actually take, it's going to take an inordinate amount of time. But I will explain sort of what's going on here, right? We have all of these movie plots that we have downloaded earlier. And what we will be doing here is we're simply going to be loading all of them, and we're going to be using a library called sentence transformers to turn those plots, to turn those pieces of text into embeddings, into these sort of high dimensional vectors, right? And once this is probably going to take quite a while on my local machine, but once you run it through these models, you'll be able to get these vectors and you'll be able to insert them into Milvus. And I simply want to show folks, after we run through all of these, we can perform a search inside of Milvus. And I simply want to show folks what the results of these are. So this is a very, very small data set. So the results are not 100% representative of everything that you see here. But if I have, for example, if I'm searching for a movie about cars, one of the top ones that comes up is Auto Driver, which is clearly a movie about cars. If I search for a movie about monsters, I get quite a few about zombies, about monsters, so on and so forth. So this is a way to be able to really recap. This is a way to be able to search across different movies from a semantic perspective. If you remember one of the earlier slides, what we want to try to be able to do with unstructured data is enable computers to understand what is going on inside of these different pieces of data. In this case, what we've done here is we've used Milvus and we've used sentence transformers as well to enable us to turn these movie plots into embeddings, and then for us to be able to query across all of those plots, not in a traditional sense, not using keywords, not using traditional methods like TF-IDF or BM25, but instead to use semantic search to search across all of these movies, all these movie plots semantically, right? And again, I didn't go over all of these, but I do encourage you to try this on your own time, run through the entire notebook. And once you do that, I think you'll be able to sort of try some of these different search terms as well. And it's really quite fascinating how your vector database is going to respond to some of these different search terms. Here, we've also prepared another notebook around image search. And again, we'll go through a very, very similar process here. Install the requirements that we need. I've already gotten the data set in this case. We provide it again on Google Drive for you to be able to download. It is a painting data set. And here, what we're going to do is we're going to set up Milvus again. In this case, as I mentioned before, I am using Zilla's Cloud. What I'll be doing here is I'm actually going to be creating a different collection. So even though it is the same database, we can actually use this database to, we can actually have different collections in this database and be able to search across these collections, different collections in the same instance. So do the same thing. We're going to connect to our database. We're going to sort of drop the previous collection and then redo that collection, create the schema that has the embedding in it, and then simply do the create an index as well. And in this case, as I mentioned before, as I alluded to earlier, this index we are going to be, Zilla's Cloud is going to be automatically selecting the index for us. We're going to then insert the data, and what I won't go through this in great detail because what we're doing here is we're pulling an image recognition model from PyTorch, and it's going to take quite a while to be able to run through all of these images locally on my local machine. But instead, I'll sort of go through some of these different, I'll sort of go through what's going on in these different cells, and then we'll look at some of the results at the very bottom. So we're taking all these images, loading them, transforming them, running them through the model, and then we're performing the search sort of in the vector database. We're going to turn these images into embeddings and be able to do all of this just like that, snap of our finger. And if I plot the results here, I probably do want to make these a little bit smaller so I can see a little bit better. Let me see. Okay, we'll keep it this way. But here, what we've done is we're simply taking. You see these images on the left here, and you see these images on the right. The three images on the right. What's on the left is the query image, and what's on the right is actually the nearest neighbor in our vector database. And you see how these are very, very. You see how I can search images with images in this case, and how I can be able to search across all that semantically. The two on the left that you see here are actually real-world photos, and what you see, the three images that you see on the right, each of these rows are their corresponding nearest neighbors based in using these image semantics. And the idea that we can actually, the key takeaway from all of this, I do realize I'm trying to cram a lot of content into a very small amount of time. But the key takeaway from all of this is that, as I mentioned, vector search, there's a lot of different strategies for vector search. And when you want to be able to do vector search at a very, very large scale, when you want to be able to do it at, let's say, a billion scale, there's a lot of challenges associated with that. How do I shard my vectors across different machines? How do I make vector search scalable in a way that is both efficient for memory as well as for compute? I also wanted a lot of traditional database features as well, right? I want to be able to do caching. I want to be able to do failover. I want to be able to do replication. And these are all things that a vector database will be able to do for you. I'm going to stop sharing here, and I'm actually going to go back to my slides. So give me one moment here. Vector database is really, I get a lot of folks who come to me and, as we develop this vector database internally, they say, oh, that doesn't seem too hard. I can, that indexing script that you wrote, HNSW, is only like 100 lines of code. I feel like I'll be able to wrap that and, run a vector database, create my vector database within a week. And if you can really do that, I strongly encourage you to talk to me afterwards, and we will figure out a way to bring you on board onto Zillaz. Because a vector database, there are so many features inside of it that simply go beyond pure vector search. As I mentioned earlier, there's replication, there's caching, there's you want a good unified SDK, you want a good API to be able to access your vector, to be able to query across your vectors, and you want really, really good, really solid performance as well. As I was doing the indexing earlier, simply in that Jupyter notebook, you saw that my performance wasn't that great, even across just 10,000 vectors. With flat indexing with prog quantization, I would have over 50 milliseconds of latency, which is probably not ideal if you want to put it in production. At the same time, oftentimes a lot of these very, very large companies and very large organizations are looking to deploy vector search at a massive scale with a large number of queries per second. And that is really a lot of the code, a lot of the logic beyond just the pure vector search component is what a vector database is there for. So, I'm sort of leaving the screen a little bit longer on here on purpose. Feel free to scan that QR code to be able to access the demo materials and the tutorials folder there. Feel free to visit our website as well, milvus.io, to take a look at the vector database that we've built, go through some more examples, and see, I strongly encourage everyone to, in addition to playing around with those different vector search strategies, to go and play around with Milvus as well. Right, that we have different versions, standalone, cluster, embedded, that you can install very, very easily on your machine. And you'll be able to query it the same way that I've queried it earlier in the notebooks. I'm going to go over very, very briefly some real world use cases. Now, these are what I consider to be some sort of smaller use cases, because I think if you really understand, once you really come to understand vector search and understand what vector databases are used for, you can see, hey, for product recommendation, it's a big one. For other things like video search for targeted advertising, vector databases are used very commonly as well across a variety of different organizations. But I just want to highlight some very, very interesting and unique ones that are really, in my opinion, show how vector databases can be used beyond just a lot of the most common use cases. So sort of our gallery experience here, with something that we did with Cleveland Museum of Art, launching ArtLens AI, and you can see an example of what's going on here in the bottom left-hand corner. Threat detection, the ability to say, I want to embed APKs or executables in the same space, be able to search and be able to detect threats that way. As I mentioned earlier, product recommendation, sort of taking, let's say, a product and taking users and embedding them in the same space that way. And then property search as well, to be able to do sort of more personalized search, more or less, to be able to search across a variety of different components beyond just saying, hey, I'm going to do keyword search across text. I'm going to find, or I'm going to do, in the case of Compass, I want to match the number of bedrooms, or I want to match the total size of property that I'm searching across.
Thank you so much, Frank. I mean, I enjoyed the discussion because, this is an area that's somewhat new for me as well. So yeah, definitely, this was a wonderful discussion. So yeah, thank you so much.
Yeah.